Hi everyone, welcome to this video lecture over section 5.8, Further Integral Formulas. I assume we finished 5.7 on Wednesday. If we didn't, this is a little out of place, but it should all be okay. So section 5.8, Further Integral Formulas. We've already covered a lot of integral formulas, but we're going to cover just a few more before we finish things out. There's a few more derivatives that we know. We're going to try and find the antiderivatives related to those. First things first, starting off really weird. So we know that the antiderivative of 1 over x is natural log of x, which is really handy. In fact, we can use that to define the natural log. Oftentimes, it's really nice to define the natural log function via the antiderivative of 1 over t. Notice here the antiderivative goes from 1 to x. We want to do that because, as we all know, the natural log of 1 should be 0 because e to the 0 is 1. Remember what a natural log is. Natural log of 1 equals 0 because e to the 0 equals 1. So in order to maintain that the natural log of 1 equals 0, we want this natural log to start at 1 and go to whatever x. That's just a little random side note that we kind of don't address again for the rest of the section, but I wanted to bring it up. I know if you ever go into like complex analysis, so if you stay in mathematics and you start working with complex numbers in the complex plane, they definitely define natural log this way. But that doesn't matter too much to us. What matters more to us for this section is inverse trig functions. So here I have the derivative of 4 inverse trig functions. I don't have secant or cosecant because they don't matter too much. What matters for us for the purposes of this class are inverse sine, inverse cosine, inverse tangent, and then to a lesser extent inverse cotangent. So, as we know, as we recall from chapter 3, the derivative of the inverse sine function, remember this sine to the minus 1 does not mean sine of x raised to the minus 1. So let me make that note right here. Sine to the minus 1 of x is not sine of x raised to the minus 1, even though, confusingly enough, sine squared of x is sine of x squared. Okay, so if this exponent here is -1, it doesn't behave like this. Okay, sine to the -1 of x is the inverse sine function, also called arcsine. Remember that the way the sine function works is we hand it an angle, and it tells us the ratio of the opposite to the hypotenuse of a triangle. The way the inverse sine function works is we hand it a ratio. We hand it the ratio of an opposite to a hypotenuse, and it tells us what angle has that sine, has that ratio as its sine. Okay. We also, back in the day, we learned these derivatives. Okay, we learned that the derivative of the sine function, of the inverse sine function, I should say, is 1 over the square root of 1 minus x squared. With this in mind, the antiderivative of 1 over the square root of 1 minus x squared dx should be the inverse sine function. And indeed it is, plus a constancy. So the antiderivative of 1 minus the square root of 1 minus x squared, all in the square root, when we take the antiderivative of that, we get the arcsine function, or the inverse sine function. Similarly, if we take the antiderivative of -1 over the square root of 1 minus x squared, we're going to get the inverse cosine function. And again, the reason why is because the derivative of the inverse cosine function is this -1 over root 1 minus x squared. Continuing in this way, if we take the integral of 1 over 1 plus x squared, we should get inverse tangent plus our constant of integration. And then lastly, if we take the antiderivative of -1 over 1 plus x squared, we should get the inverse cotangent function plus c. So really what we're doing here is we're taking derivatives that we know and we're just running them the other direction. right? We already know that if we start with inverse sine and we take the derivative, we get to 1 over root 1 minus x squared. Now we're starting with 1 over root 1 minus x squared, taking the antiderivative to get back over here to get the inverse sine function. Okay, these are things that you might want to remember. All right, let's take a look at a problem that might use these. So here's an example. We want to find the antiderivative, or the area under the curve from 0 to 1 of x squared plus 1. Notice here I have this dx in the top. That's totally fine. This is the same as the integral from 0 to 1 of 1 over x squared plus 1 dx. Just oftentimes people write it like this to condense things to make it a little bit smaller. It's totally the same as this. I personally tend to always write it like this. I like my dx at the end if I can help it, if I can get it that way. Okay, so how do we solve a problem like this? Well, we know we're going to take an antiderivative, we're going to plug in our bounds, we're going to do some subtraction, we're going to call it a day. So the question is, what is the antiderivative of 1 over x squared plus 1? What is the antiderivative of 1 over x squared plus 1? Well, this is something we memorized just 10 seconds ago, 20 seconds ago, whatever. We know that the antiderivative of 1 over 1 plus x squared is the inverse tangent. You know, here I have x squared plus 1, but that's the same as 1 plus x squared. So we know that this should be the inverse tangent of x evaluated from 0 to 1. And then this evaluation from 0 to 1, that's going to give us the inverse tangent of 1 minus the inverse tangent of 0. Now, how can we figure these out? Inverse tangent of 1. What angle, when I plug it into the tangent function, gives me 1? Well, the angle is 45 degrees, or pi over 4. So the inverse tangent of 1 is pi over 4. And what about the inverse tangent of 0? What angle, when I plug it into the tangent function, gives me 0? Well, let's remember that tangent is sine over cosine. So because I'm going off on a tangent, I'll use a different color. Okay, and so if we're looking for an angle that makes tangent of x equal 0, well, that's something where sine of x over cosine of x equals 0. That happens when sine of x equals 0. So what value of x makes sine equal to 0? Well, the answer is 0 degrees, or 0 radians. So the inverse tangent of 0 is 0, because if I plug 0 into the regular tangent function, I get 0 back. So my final answer here will be pi over 4 minus 0 gives me pi over 4. One more time to reiterate, the reason, again, I'll change color here. The reason the inverse tangent of 1 equals pi over 4 is because the tangent of pi over 4, if I plug pi over 4 into the regular tangent function, I get 1 as my output. The inverse tangent and the tangent function, they undo each other. So if I take the tangent of pi over 4, I get 1. And that means if I take the inverse tangent of 1, I'll get pi over 4. Cool. Let's take a look at another inverse trig example. Here I have the integral. Oh man, I need to have bounds on that one. What bounds do I need to have? I need to have the bounds from 0 to 3/4. The bounds from 0 to 3/4. Should I edit this out? No. So we have the integral from 0 to 3/4 of dx over root 9 minus 16 x squared. Again, I'm going to move this dx to the side. That's totally okay. We get 1 over root 9 minus 16 x squared dx. Now, how do we take this integral? I mean, I don't know what the antiderivative of 1 over root 9 minus 16 x squared is, but maybe we can find out. One thing I do know, let me rewrite this 16 because it's not very good looking. There we go. That's a good looking 16. So how do I take this? I don't know the antiderivative. One thing I do know on, again, a little tangent, a little side note, is I know that the antiderivative of 1 over root 1 minus x squared is inverse sine. I know that for sure. And why that's helpful is this here, this 1 over root 9 minus 16x squared, looks kind of like this. Plus or minus some amount of constants. So I think to myself, this looks like this. Is there something I can do to make it really look like this? Is there something I can do to get rid of this 9 here and turn this 9 into a 1? Yeah, we can factor out a 9, right? So we get the integral from 0 to 3/4 of 1 over the square root of 9 times 1 minus 16 over 9 x squared. Why am I factoring out a 9 again? Let's remind ourselves. I'm factoring out a 9 to try and make this term here look like this term. So I want a leading 1 here. The reason I'm trying to get this to look like this is because I know how to take this antiderivative. I don't know how to take this antiderivative, but if I can massage it a bit and kind of turn it into this guy, then I can take that antiderivative. Okay, so let's continue simplifying down here. This gives me the antiderivative, or the integral, from 0 to 3/4 of 1 over square root 9 times square root 1 minus 16 over 9 x squared dx. What's nice about that, the reason I can do that, let me clarify, is that square roots break apart over multiplication and division. So the square root of 9 times something is the same as the square root of 9 times the square root of that thing. Okay, and I know the square root of 9 is 3, so I can do that. And now I end up with, I'm going to simplify this a little bit more, I end up with the integral from 0 to 3/4 of 1 over 3 times the square root of 1 minus 4 over 3 x squared dx. Why did I do that? Why did I write this 4 over 3 x squared? Well, remember, what I want is 1 minus some term squared. Okay, I don't want any coefficients in front of this x here. I don't want any coefficients in front of the term. So what I have now is 1 minus some term squared. Now this term does have a coefficient, but we can get rid of it via a u substitution. And that's exactly right. So I'm going to use u substitution to try and get rid of this 4/3 because it's inconvenient to have that coefficient out in front. So I'm going to let u equal 4/3 x. So then du dx equals 4/3. And this tells me that, rearranging both sides, I get du equals 4/3 dx. And then lastly, this tells me that 3 over 4 du equals dx. Okay, this is just similar to u substitution that we should have covered by now, hopefully. So I can plug this in here, and I can plug u in here. And so this is going to give me the integral as x goes from 0 to 3/4 of 1 over 3 times the square root of 1 minus u squared times 3 over 4 du. So just plugging in u for 4/3 x here, and plugging in 3/4 du for dx. Okay, almost done. We can do a little bit of simplification. I have this 3 on top and this 3 on bottom are going to cancel out. And so this leaves me with the integral as x goes from 0 to 3/4 of 1 over 4 times square root of 1 minus u squared du. And for full clarity, this is the same as 1/4 times the integral as x goes from 0 to 3/4 of 1 over root 1 minus u squared du. All right, so we massaged our integral a lot. We started with this weird-looking thing, dx over square root 9 minus 16x squared. We went step by step. We brought the dx outside, so we were left with this fraction. And we thought, hey, that looks kind of like 1 over root 1 minus x squared. How can I make it look fully like 1 minus root 1 over x squared? So we began by getting rid of this 9 by factoring out a 9. And this left us with square root of 9 times 1 minus 16 over 9x squared. We could factor out the 9, and we got 1 minus some term squared. And then in order to make sure that term just didn't have a leading coefficient, we used u substitution to try and get rid of that 4/3. Using this u substitution, we ended up with 1/4 times the integral as x goes from 0 to 3/4 of 1 over root 1 minus u squared du. And we know this antiderivative. This is the inverse sine, right? So this gives us 1/4 times the inverse sine of u evaluated as x goes from 0 to 3/4. Okay, we can multiply the constant back in. So probably for ease, this is just 1/4 times inverse sine of u evaluated as x goes from 0 to 3/4. Notice now the 1/4 is inside the parentheses, so it's part of the evaluation. Now, I cannot directly plug in 3/4 and 0 in here. Okay, because remember the 3/4 and 0 correspond to x values. What I have here is a u value, so I just need to trade my u back in for my x, and we're off to the races. So this is going to give me 1/4 times the inverse sine of 4/3 x, because u equals 4/3 x. So 4/3 x evaluated as x goes from 0 to 3/4. And now we can plug in and do our calculation. We get 1/4 times the inverse sine of 4/3 times 3/4, plugging in x equals 3/4, minus whatever I get when I plug in 0. 1/4 times the inverse sine of 0. Okay, 4/3 times 3/4, that's just going to give me 1. So I'll go ahead and erase this now to give me 1. So what is the inverse sine of 1? What angle, when I plug it into the sine function, gives me 1 as an output? Well, it's pi over 2, because the sine of pi over 2 is 1. So we get 1/4 times pi over 2 minus, and now the inverse sine of 0, how can we find that? What angle, when I plug it into the sine function, gives me 0? 0, right? The sine of 0 is 0. So this is minus 1/4 times 0. That gives me 0. So my final answer is 1/4 times pi over 2, which is pi over 8. Awesome. Now for something a little bit different. We learned how to take the derivative of b to the x. What is the antiderivative of b to the x? Where here b is just some constant. I'm using b for base. But let's remind ourselves that the derivative of b to the x equals natural log of b times b to the x. Okay, so for example, the derivative of 3 to the x is going to be the natural log of 3 times 3 to the x. So with that in mind, can we find a function whose derivative would just be b to the x with nothing else, no natural log terms or anything. And if you think about it for a bit, you'll probably come up with a function. We need something that eventually cancels out this natural log 3. And one way to do that is to start out with b to the x over natural log b. So we divide by natural log b in our function, and we can verify that this is indeed correct by taking the derivative of b to the x divided by natural log of b. This is going to give me 1 over natural log of b, just separating this guy out here, the constant, times the derivative of the top, times the derivative of b to the x, which as we know is natural log b times b to the x. And huzzah! Our 1 over natural log b and our natural log b cancel out, and we're left with b to the x. What does that mean for us? What that means for us is that the antiderivative of b to the x is b to the x divided by natural log of b. So that's something that we might want to commit to memory. Okay, let's use that in a problem, right? Let's do that to actually solve something. What I have here is I want to find the area under this curve, under the curve 7 to the x, between x equals 3 and x equals 5. We do this, of course, by taking an antiderivative, plugging in 5 and 3, and then subtracting what we get. So, what is the antiderivative of 7 to the x? Well, we know that the antiderivative of anything, any base to the x, is going to be b to the x over natural log b. Here, my base is 7. So this is going to work out to be 7 to the x divided by natural log 7, evaluated from 3 to 5. So this is going to give me 7 to the 5th over natural log 7 minus 7 to the 3rd over natural log 7. We can combine those because they have a common denominator. We get 7 to the 5th minus 7 to the 3rd over natural log 7. I don't know what that number is, but that's a number. Let's look at a more complicated example, maybe something a little bit less straightforward. Here's one. We're going to take the antiderivative, or the integral, from 0 to pi over 2 of cosine theta times 10 to the sine theta. What do we do? Well, we know how to take the derivative of 10 to the x, so it'd be really handy to get this function to look like 10 to the x. The problem is we have this extra cosine theta floating around. Is there anything we can do about that? Yeah, right, we can use u substitution. Right, we can let u equal sine theta. Well, then du d theta equals cosine theta. Manipulating both sides, we're going to get that 1 over cosine theta du equals d theta. Okay, we found that by multiplying both sides by d theta and then dividing both sides by cosine theta. So plugging that stuff in, we get the integral as theta goes from 0 to pi over 2 of cosine theta times 10 to the u times 1 over cosine theta du. So again, I'm just plugging in u for sine theta here in the function, and I'm plugging in 1 over cosine theta times du for d theta here. Luckily, our cosine theta and our 1 over cosine theta cancel out, and so we're left with the integral as theta goes from 0 to pi over 2 of 10 to the u du. What's this? Well, we just learned, right? This is going to give us 10 to the u divided by natural log of 10. And we're going to evaluate as theta goes from 0 to pi over 2. Now, again, note, I can't plug in 0 and pi over 2 directly in here and evaluate, because here I have the variable u, and here I have the variable theta, but we can trade in our u for theta and call it a day. Remember that u equals sine theta. So this is the same as 10 to the sine theta over natural log of 10, evaluated from pi over 2 to 0, or from 0 to pi over 2. Now let's do the plugging in. This gives me 10 to the sine of pi over 2 over natural log 10 minus 10 to the sine of 0 over natural log 10. We have a common denominator, so we can combine. This gives me 10 to the sine of pi over 2 minus 10 to the sine of 0 all over natural log 10. And we can compute this further. The sine of pi over 2 is 1, and the sine of 0 is 0. So this gets me 10 to the 1 minus 10 to the 0 over natural log 10. So this is 10 minus 1 over natural log 10. This is 9 over natural log 10. So a little bit of u substitution, a little bit of antiderivative of b to the x, and we can call it a day. And that's all that I have. That's the last example for the semester, assuming that we finished 10.7 on Wednesday. And if we didn't finish 10.7 on Wednesday, then we've got some more u substitution examples for Monday. But thank you so much for your time and attention.